I'm going to use this table now to do our subtraction. We need to reference it because we're now using 8 bits. It was nice and easy when it was 3 bits. There was only 8 values. When it went to 4 bits, there was 16 values. But now I'm at 8 bits. There's 256 values. As you can see, it's getting a little bit too large to have a table. But this is probably the largest we could have a table, and we'll use it, and I'll show you how these numbers work out. So hopefully you are okay with the fact that for the negative numbers I've started at the very end, all the ones, to start off with -1 and then worked my way up until the last one was -128 and the next one along back into the positives. So here we go. Here's my sum that I want to work out. 50 take away 100. Now, if you work that out on the calculator or in your head, 50 take away 100 is -50. So let's take a look at that in binary again. So 50 is a positive number. So here I've got the positive number. It starts with 0, and this is its bit pattern. 0, 0, 1, 1, 0, 0, 1, 0. I have put that down there. The next number I need is -100, -100. So I look in my table for -100 and I write its bit pattern down, and that is 1, 0, 0, 1, 1, 1, 0, 0. Now I just add the two numbers together because every time we do subtraction we're just adding. So nothing plus nothing is nothing. 1 plus nothing is 1. Nothing plus 1 is 1. Nothing plus 1 is 1. 1 plus 1 is 2. So that's write down the 0, carry the 1. 1 plus nothing is 1. Plus 1 is 2. So write down the 0, carry the 1. 0 plus 0 is nothing plus the carry 1. And finally, nothing plus 1 is 1. And that is my answer in 8 bits. And if I go back and take a look in my table for this bit pattern, 1, 1, 0, 0, 1, 1, 1, 0, we can see that that is -50. So that's how to do sort of subtraction using addition in binary. At the very start, I had in red this word, 2's complement. The table is fine. As I said, the 256 values I could just about manage. But if I went up to a 16-bit computer, 2 to the power 16 is 65,536 different items. I can't even begin to think of the time I would need to actually write out this table. Half of them would be positive, half of them would be negative. So if I were using signed binary numbers where the most significant bit is used for the sign, I'd have 32,768 positive numbers and 32,768 negative numbers. That's a lot of numbers to write down in a table and to label up -1, -2, -3 and so forth. I need a better method. The positive numbers would range from 0 to 32,767, and the negative ones would range from -1 to -32,768. If you don't understand where I've got these numbers from, go back, have a look at the simpler version with 3, 4 or even 8-bit computers. I am not going to be doing 16-bit calculations. I just wanted to point out that there is a point where having a table, a lookup table, is of absolute no use to us. We would spend too long writing out the table. So we need a method, and that method is called 2's complement. And in the next video, I'm going to start looking at how you manage 2's complement.